Welcome dear students into the class of number theory, and today in this video I am going to start the concept of congruences. So let us first understand what is the meaning of congruences. If a, b and m are integers, then we say that a is congruent to b modulo m if m divides a minus b. That means a minus b is a multiple of m. For example, you can say that 7 divides, you know that 7 divides 19 minus 5. 19 minus 5 is 14 and 7 divides 14 is clear. And it means your 19, this 19 is congruent to 5 modulo 7. This is the notation. If a is congruent to b modulo m, we write a, this is the sign of congruent, a is congruent to b modulo m. Here you can say that 19 is congruent to 5 modulo 7. So this is the definition of congruence, and now we will move on to some properties. Actually, this congruence is a relation between two integers a and b modulo m, where m may be any integer. So this relation we will check whether it is reflexive, symmetric, transitive, that means is it equivalence relation or not, and then we will move ahead. So first of all we will check whether this relation is reflexive, is it symmetric, is it transitive. So the first one is reflexivity. We know that reflexivity means a is related to a is congruent to a modulo m, where m is an integer. So a congruent to a modulo m, is it true? Yes, it is true, because what it means m divides a minus a, and it means m divides 0, and it is true, we know that, because 0 is divisible by every integer. So this a congruent to a modulo m is true. That means this relation, congruence relation, is a reflexive relation. Let us move on to the next one, symmetricity. So symmetricity. If a is congruent to b modulo m, we have to check if b is also congruent to a modulo m or not. So that is again very easy process. A congruent to b modulo m means m divides a minus b. And if m divides any integer, then m must also divide its negative. So this means m divides negative of a minus b. And that means m divides b minus a. And if m divides b minus a, this means your b is congruent to a modulo m. That means whenever a is congruent to b modulo m, b is also congruent to a modulo m. So the relation is symmetric. This is a reflexive relation, this is a symmetric relation, and now let us check whether it is transitive or not. So the third is transitivity. For transitivity, let a be congruent to b modulo m and b be congruent to c modulo m. We have taken a congruent to b and b congruent to c modulo the same number m. So we will see whether a is congruent to c modulo m or not. If it is, the relation will be transitive, otherwise it will not be. Now a is congruent to b modulo m means m divides a minus b, and b is congruent to c modulo m means m divides b minus c. Now m divides a minus b and m divides b minus c, and we know that if m divides two numbers, then m must also divide their sum. So this means m divides a minus b plus b minus c. B will be cancelled out and you will left with m divides a minus c, and m divides a minus c means a is congruent to c modulo m. We have taken a congruent to b modulo m and b congruent to c modulo m, and what we obtain is a congruent to c modulo m, which makes this relation, the relation of congruence, a transitive relation. So this is a reflexive relation, this is a symmetric relation, this is a transitive relation as well. And we know that if a relation is reflexive, symmetric as well as transitive, then it is called an equivalence relation. And for equivalence relation, definitely there must be equivalence classes. So equivalence classes will be for modulo M. For modulo M, what the equivalence classes will be. So you start writing the numbers starting from 1, 1, 2, 3, 4, move on to M, and then restart with M plus 1, M plus 2, M plus 3, M plus 4, here you will get 2M, and once again 2M plus 1, 2M plus 2, 2M plus 3, 2M plus 4, and so on up to 3M, and so on. 3M plus 1, 3M plus 2, 3M plus 3, 3M plus 4, 4M. At some stage you may get NM plus 1, NM plus 2, NM plus 3, NM plus 4, and so on. Here you will get N plus 1 times M. So here are your equivalence classes. This is your first equivalence class. Because if you take any two numbers in this class, suppose I am taking 3M plus 1 and M plus 1, then they are congruent to each other modulo M. 3M plus 1 is congruent to M plus 1 modulo M is very clear, because the difference of these two is 2M, which is divisible by M. So M divides their difference. That means these two are congruent to each other modulo M. Similarly, if in this set you take any two elements, they will be congruent to each other. Similarly here, similarly here, similarly here. But if you take one element from here, another from here, they will never be congruent to each other modulo M. So in this fashion you can construct the equivalence classes for the relation of congruence. This was the very fundamental results, and now we'll move on to some more very easy and very fundamental results related to these congruence relation. Let us see what these relations are, what these fundamental properties are, and we'll prove these of course one by one. So I am writing here A, B, C, D are any integers. M is any integer. M is not equal to 0, obviously, because we have to take modulo M. We can't take modulo 0. Always we will take modulo non-zero quantity. So I am taking M as non-zero quantity. And now some results we will prove. The first result where I am going to prove that if A is congruent to B modulo M and D is a divisor of M, then A is congruent to B modulo D also. So this is the first result what I am going to prove here in relations with the congruence relations. What we are given with? We are given that A is congruent to B modulo M, that means M divides A minus B. And we are also given that D divides M. This is also given to us. Look carefully, D is a divisor of M and M is a divisor of A minus B. Is it not means that D is also a divisor of A minus B? Yes, it is. If D divides M and F divides A minus B, then directly it means that D divides A minus B. And if D divides A minus B, then by definition of congruences, it follows that A is congruent to B modulo D. So here is the first very trivial result about congruences. So let us move on to another result. I'll prove some 4 or 5 results and then I'll leave you to practice these all results. The second what I'm going to take is, if A is congruent to B modulo M, then leave this if, A congruent to B modulo M implies that AC is congruent to BC modulo M for every C belonging to the set of integers. And the proof is once again very easy. We are given that A is congruent to B modulo M, which directly means that M divides A minus B. If M divides A minus B, then definitely M divides all the multiples of A minus B also. So I am taking C multiple of A minus B. So this means M divides C times A minus B. If M divides A minus B and it is a multiple of A minus B, if M divides a number, then M divides its multiple also. So M divides C times A minus B, and this means M divides CA minus CB. And if M divides CA minus CB, then by the definition of congruences, CA is congruent to CB modulo M. So another trivial result is being proved for congruences. Let us move on to more results. These are the properties which we will use later on while we are solving the questions related to congruences. The next one I am taking, A is congruent to B modulo M and C is congruent to D modulo M implies A plus C is congruent to B plus D modulo M, which is again very easy. What we are given with? We are given with these two. A is congruent to B modulo M, means M divides A minus B, and C is congruent to D modulo M, means M divides C minus D. And if M divides two numbers, then M must also divide their sum. So this means M divides A minus B plus C minus D, which you can also write as M divides A plus C minus B plus D. If M divides difference of these two numbers, then these two numbers are congruent to each other modulo M. So this means your A plus C is congruent to B plus D modulo M. So it was another trivial proof and a trivial result with relations to congruences. Move on to another one. We have proved here that the sum of two congruences is also a congruence. Now what about product? If A is congruent to B modulo M and C is congruent to D modulo M, then the product AC is congruent to the product BD modulo M, and this time the proof is not so trivial. It's easy, but it is not so trivial as it was in the case of addition. In case of product, we will have to take one more step. Once again, we are given that A is congruent to B modulo M, that means M divides A minus B, and similarly M divides C minus D. Now M divides A minus B means A minus B can be written as M times K1 for some integer K1, and M divides C minus D means C minus D can be written as MK2 for some integer K2. From here you can find the value of A is B plus MK1, and from here you can find the value of C is equal to D plus MK2, and now multiply AC. Now what is your AC? Value of A is B plus MK1 and value of C is D plus MK2. So multiply these, you will get AC is equal to BD plus you will get M times BK2 plus DK1 plus MK1K2, and you can write AC minus BD is equal to M times L1. This quantity I am renaming it as L1. It is an integer. So AC minus BD is a multiple of M. That means M divides AC minus BD. And if M divides AC minus BD, then clearly by definition of congruences, AC is congruent to BD modulo M. So if A is congruent to B modulo M and C is congruent to D modulo M, then the product AC is congruent to the product BD modulo M also. So this was another result, very good result, which will be used later on. in the chapter of congruences, when we will be dealing with some typical questions. And I'm going to prove another very important result which will be used later on, that if A is congruent to B modulo M and N is any positive integer, N is greater than 0 and N is an integer, then A raised to the power N is congruent to B raised to the power N modulo M. That is another very easy result to be proved, but not so trivial. It is easy but not so trivial. Once again we are given that A is congruent to B modulo M, which means M divides A minus B. And if A divides M divides A minus B, then definitely M divides any multiple of A minus B. So I'm multiplying this A minus B by A raised to the power N minus 1 plus A raised to the power N minus 2 times B plus A raised to the power N minus 3 times B square, plus and so on. I'll move up to when I'll get B raised to the power N minus 1. And if you look at carefully at this term, open this bracket, what you are going to get? You are going to get nothing but A power N minus B power N. And M divides A power N minus B power N directly means A power N is congruent to B power N modulo M. So that means what we have proved? We have proved that if A is congruent to B modulo M, then A square is congruent to B square modulo M. A cube is congruent to B cube modulo M. A power 4 is congruent to B power 4 modulo M, and so on. This result we have just recently proved, and now I'll use this result to prove another very important result. The next I'm going to prove is that if f is any polynomial with integral coefficients and A is congruent to B modulo M, then f of A is also congruent to f of B modulo M. This result we are going to prove it, and in proving this we will use the result just proved now, that if A is congruent to B modulo M, then A raised to power N is congruent to B raised to power N modulo M also. That result we are used to prove this result. So let fx be, since fx is a polynomial with integral coefficients, so let fx be equal to a0 plus a1x plus a2x square plus and so on plus apx raised to the power p. So p is the degree of the polynomial I have taken here. This is your fx. So what will be your fa? Now your fa is a0 plus a1a plus a2a square plus a3a cube plus and so on plus ap a raised to the power p. This ap is a coefficient and this a power p is the product of a p times. And what is your fb? Your fb is a0 plus a1 times b plus a2 times b square plus a3 times b cube plus and so on plus ap times b raised to the power p. Now we are given that A is congruent to B modulo M. This is given to us. I am just using the previous result now to prove it. A0 is congruent to A0 modulo M is okay. A0 is congruent to A0 modulo M is okay. Why okay? Because reflexivity. The relation of congruences is a reflexive relation. Every integer is congruent to itself. So A0 is congruent to A0 modulo M is okay. Now A is congruent to B. So A is congruent to B modulo M. It is given to us. And we know that if A is congruent to B, then AC is congruent to BC. Proved in the second part recently just now. So C I'm going to take as A1. So that means A1A is congruent to A1B modulo M. So this is your C. AC is congruent to BC modulo M. Once again, A is congruent to B modulo M. So that means A square is congruent to B square modulo M, because A power n is congruent to B power n modulo M, and I am taking here 2. Once again, this is congruent to this, and multiplying by the same constant C both sides is okay, because of the second part just proved now. So now C I am taking as A2. So A2 A square is congruent to A2 B square modulo M, and so on and so on. What you will get, and so on, you will get AP A raised to the power P is congruent to AP B raised to the power P modulo M. And we know that if A is congruent to B and C is congruent to D, then their sum is also congruent modulo M. So adding all these congruences, what you are going to get? Add all these congruences. When you will add these, A naught plus A1A plus A2 is A square and so on plus AP A power P, you will get nothing but FA. So sum of all these is FA is congruent to, and similarly sum of all these A naught plus A1B plus A2B square plus and so on AP B power P, it is your FB. So FA is congruent to FB modulo M, and that was the required result to be proved. We have proved the result finally. So I'm going to stop this video here. In the next video we will have more and more properties to be discussed on congruences. Till then, thank you once again.